Hello and welcome to today's e-showcase, the first-hand operating experience of ANITA Mox deammonification through long-term pilot studies at Sioux City and LA County Sanitation Districts. I would like to thank today's sponsor, Veolia, for sponsoring today's event. Our speakers for today will be Larry Lee, Product Manager, Veolia Water Technologies, Yang Ojin, Utilities Program Manager, City of Sioux City, Anna Long, Project Engineer, LA County Sanitation Districts, Michael Liu, Supervising Engineer, LA County Sanitation Districts. And now I'll hand the presentation off to our presenters.
Regina, should we give it a couple of minutes or we start now?
Yes, you can start your presentation.
Okay, welcome everybody to our presentation today. My name is Larry Lee. Thank you, Regina, for the introduction. I just wanted to give a quick introduction of the ANITA Mox deammonification technology. For those of you who know the technology well, this is probably a repeat, but for those of you who are not familiar with the technology, you might find this a little helpful. So we're going to go over principle, how the system, what the system consists of, and also I'll give you guys a project update on ANITA Mox. Next slide, please. So as we all know, you're looking at a picture of a typical wastewater treatment plant. On the top, you have the liquid treatment, mainstream treatment train. And on the bottom, you're looking at the side stream, the sludge handling process. So ANITA Mox is used in the side stream portion of the plant where it treats the centrate or the filtrate out of the anaerobic digesters. The ANITA Mox technology, it helps remove ammonia and also total nitrogen directly from the centrate before it goes back to your liquid treatment process. There are quite a few benefits we're going to talk about later to handle the centrate, to remove the ammonia and total nitrogen before it goes back, because it's more efficient to take the ammonia and the total nitrogen out through the side stream because it uses less oxygen. It also uses less carbon. The other benefit it has is it produces less sludge. So we're going to talk about that more later. Next slide, please. So this is the principle for the ANITA Mox deammonification technology. As we all know, the traditional total nitrogen removal pathway is you convert ammonia to nitrite, and then you convert nitrite to nitrate, and then on the way back you denitrify the nitrate to nitrite, and then from nitrite you go to a nitrogen gas. So it's a long pathway, and along the way you need a lot of aeration energy, and also you need to add a lot of external carbon if your influent doesn't have a lot of BOD. The new path for the ANITA Mox, now it's a shortcut. If you look at the graph here, it goes from ammonia to nitrite, but it doesn't go to nitrate anymore. So the anammox bacteria will combine the ammonia and the nitrite and convert those to nitrogen gas directly. So a good analogy is like if the conventional pathway for the nitrogen removal is like climbing Mount Denali. If you think about it, Mount Denali is pretty tall, so you need a lot of oxygen. and also you need a lot of food, which is BOD, in order to climb up and climb down the mountain denali. But the new pathway, the ANITA Mox, will be like, walking over the Kill Devil Hills here, which is a very small mount. It does not take as much oxygen. It does not take as much carbon, and at the same time, it produces way less sludge. So there's a lot of benefits to this ANITA Mox technology. Next slide, please. So basically, there are two modes for the ANITA Mox system. One is MBBR, the other is IFAS. The MBBR is used for regular centrate without co-digestion, without THP pre-treatment. The MBBR is the most simple technology on the market because it's a flow in, flow out, flow through system. It uses this anammox K5 media, which has the size of a quarter. And the media and the whole setup has been used in the regular moving bed bioreactor technology for many, many years and in thousands of installations. So it's a proven setup. For the IFAS, so it's got the benefits of both biofilm and also suspended growth benefits. So the IFAS system is used for dealing with THP or co-digestion waste where there's a lot of refractory COD or refractory nitrogen species where it's hard to, hard on the biofilm. That's why, we use the suspended growth to deal with that refractory part of the influent. Next slide, please. So for those of you who have biofilm technologies or are familiar with biofilm technologies, the inherent benefits of biofilm technology is it's simple and it's very stable and robust. It's an operator-friendly technology because of the simpleness of the technology. It's resilient and it works with flexible dewatering schedules. So these little carriers, they serve like houses for people, right? So when there's a lot of food, the bugs will eat some food, and when there's no food, the bugs will just sleep in the house, just like young people nowadays, hey, sleeping in or playing video games. But at the same time, they're well protected by the carrier. They don't need a lot of attention from their parents, just, The other benefit for the biofilm technology is it's very tolerant to high TSS, polymer, DO, variations in the influent characteristics of the centrate. The biofilm is well protected by the housing, very little risk of anammox washout. And the other benefit for the technology is we can use existing tanks. So if you have any sort of tankage available at the plant, we can retrofit that tank into an ANITA Mox side stream system. Another benefit of the system with the media is that you, as your load and flow increase, you can add more media. So you can take a phased approach in order to deal with increased load and flow in the future. And at the same time, if your load and flow further increase, you can convert the MBBR into an AFAS. So it's a really good approach for expansion. Next slide, please. Just wanted to provide a quick update on the project. So in the past 10 years, Veolia has had about 38 projects. In the U.S., we have about 10 projects so far. Just wanted to thank all the consultants and municipalities for the trust and for believing in the technology. And for those of you who have the installations, we hope we met your satisfaction. For those that are yet to be delivered, we strive to provide the best service to you guys, and we appreciate all the project opportunities and the trust. Another thing I encourage most of you guys talk to these plants, any one of these plants, and if you can learn anything from these plants, that would be great. That would be helpful to everybody. So that's all I got. Without further ado, I'll hand it over to Yan.
Next slide, please. Yeah, thanks, Reddy. My name is Yang Oh-jin, and I'm working for the City of Sioux City as a utility program manager. Actually, my primary responsibility is managing Sioux City renewable fuel project that cleans low biogas and compress and inject into the natural gas pipeline, including EPA compliance works. The reason why I started this study was I got American Recovery and Investment Act fund to develop and modify Sioux City's nutrient reduction strategy. So this study is one option of nutrient reduction strategy alternatives and funded by ARRA. Next, please. Yeah, let me start my presentation. Sioux City wastewater treatment plant is treating roughly 13 MGD and serve 5 communities from 3 different states, including Sioux City, South Sioux City, North Sioux City, and Dakota Dunes and Surgeon Grove, and 2 EPA regions like EPA region 7 and 8. Very strange area. And Sioux City wastewater treatment plant is serving almost 105,000 people, including 40 more industrial users and 400 more food service economies. The US EPA said Sioux City has the largest concentration of food industry in the United States. That's why we can see very strange influence characteristic. Next, please. This is the sky view of Sioux City wastewater treatment plant. So it is originally constructed in 1961 and had few major improvements. Wastewater get into the headworks and here in the influence characteristics, and there is almost every average value from 2020. So if you see that we have almost 784 ppm of BOD, it's huge, and 102 of TKN and 12.5 ppm of TP. Since we had really large concentration of the food industry in the United States, the influent BOD and TKN and TP concentration are very, very high compared to any other wastewater treatment plant. So the wastewater is passing through the primary clarifier where almost like 35 of BOD would be removed, and then it's flowing to the aeration basin. We have 6 basins and it's operated by emery process. And then the mixed liquid is going to the secondary clarifier and the liquid is heading to the chlorination contact chamber. After chlorination and dechlorination, the treated water was discharged into the Missouri River. The primary sludge is directly to the anaerobic digester, but the activated sludge was dewatered by RDT and then injected into the anaerobic digester. We have 4 primary and 4 secondary digester, but we will upgrade 2 secondary to primary within 2 years. The digested sludge is dewatered by the centrifuge and then applied to the land as fertilizer. Here is our effluent characteristic. As you see, we achieve almost like higher than 90% of TKN removal and 89% of TP removal. Next, please. This slide shows the history of plant upgrade for the byproduct. Currently, we are discharging treated water into Missouri River. In case of solid waste, we are producing almost 160,000 gallons per day, but all must go to the anaerobic digester to minimize the volume and to stabilize it. But before 2016, the dewatered sludge went to the landfill, but after the landfill management company changed their strategy, and then from 2016, we have to join the biosolid land application program with Class B sludge. In the near future, we will convert this Class B sludge into the commercialized commercial fertilizer that should be Class A. And the centrate is directed to the headworks so far, but in the near future, we want to apply advanced technologies such as like anammox process. For the feasibility study, we tested anammox pilot for more than a year and LG pilot for more than 6 months. In case of biogas, all the biogas was flared before, but from November 2020, we are converting the biogas into renewable natural gas and injecting into the natural gas pipeline. Next, please. Now I'm going to talk about the reason why we initiated this pilot test. As I said before, IDNR started a neutrality reduction strategy, and City submitted the first report to IDNR in 2017, but IDNR requested some more feasibility study since there were several interruptions such as industrial wastewater flow change and 2018 flood in this area. So we proposed the grant and awarded to find out alternatives for neutrality reduction in our plant. The final report deadline is December 2021, this year, and City would start to design the best alternative this year. And the neutrality reduction strategy targets are either 10 milligram per liter of TN and 1 milligram per liter of TP in final effluent, or 66% of TN and 75% of TP removal from the influent. Next, please. So our target wastewater is centrate, and this is really good for the anammox process, I think. So if you see the BOD, it's only like 205, but TKN and alkalinity is pretty high, especially the alkalinity is good enough to remove all the TKN. So we had several meetings with anammox technology providers, but the main reason we selected ANITA Mox pilot was the media. So previously, we used belt filter press for dewatering process, but we switched it to centrifuge system to increase the solid contents. Based on my previous experience, in case of high TS or TSS influence cause, that cause a lot of really critical issue in anammox reactor. I expected that that would not happen in NBBR system, and I was pretty sure that an anammox process can easily treat centrate in general, but I want to double check and make sure whether there is any unexpected issue or not. Next, please. Next slide, please. Yeah, the pilot system consists of EQ tank and feed pump and ANITA Mox reactor and air compressor. The active volume of reactor was almost 800 gallon, and the media was filled as 40% based on the active volume. And the ANITA Mox reactor was in the trailer, but all other were installed in centrifuge building. Next, please. Our target was like similar to any others, like 80% of ammonia removal and 70% of TKN removal under 0.6 gallon per minute of feed flow. And that is almost like 1 day HRT in our system. Roughly, we had about 6 weeks startup period and about 1 year of the steady operation and robustness testing. Next, please. In startup phase, we started with almost 0.2 gallon per minute of feed and almost 900 milligram per liter of ammonia. During that period of time, our centrifuge system was under the commissioning stage. So that's why we had anammox concentration of centrate was up and down. And for almost 2 weeks, we used intermittent feed, and after that, we operated continuous feeding and aeration. The removal rate was between 65 to 90% of ammonia. Next, please. I think during the steady operational period, the ammonia removal rate was between 70 to 90%. Sometimes it leads to almost 100%. The operation was pretty stable, and especially the anammox activity was pretty stable. And during the period of time, we had several unintended and unexpected stress conditions, such as cold weather, sensor failure, and compressor shutdown, and the clogging issue for feed pump. Most of the issues were due to the size of the plant. In case of weather or temperature issue, I think that would not happen in full-scale reactor. And the compressor shutdown was caused by the extreme cold weather. I think during the winter season, we had H2S issue in centrifuge building. So we had to open the door. That resulted in temperature down in the building, and the compressor shut down, and centrifuge centrate temperature was down. And the feed pump clogging issue happened due to the high TSS or TS and big size of debris, but it did not happen in big size pump for full scale, I think. Next, please. Next, please. Here's some positive outcome. I think there was no anammox bacteria washout under high TSS condition in influent. Sometimes we experienced almost 3,400 milligram per liter of TSS. The ammonia removal performance was pretty good, especially when we had no feed due to pump clogging. The effluent ammonia was almost zero. That was possible since there was enough alkalinity in our system. Under high TSS loading in influent, the pilot was operated with a stable condition. We never had any experience of NOB interference. And that is very important for long-term application. As I said, we had several stress conditions, but the pilot had recovered microbial activity within just 1 or 2 or 3 days. Next day, please. Next, yeah. Here are some representative stress conditions during the experimental condition. Especially, we may need to pay attention to strobite formation or strobite control for the full-scale application. Otherwise, it's easily overcome in full-scale system. Next, please. Here are some other issues, like in case of sensor failure, actually, at that time, we didn't spend much time to maintain this pilot scale. So maybe we need to spend more maintenance efforts in the future. And then in some case, we had a starvation condition due to the feed pump clogging issue. Once the flow went back to normal, we could not see any loss of anammox activity. So that's really important. And when we have BOD spike, most of DO was used for BOD removal, and there was not enough DO for AOB. So that results in high effluent ammonia. I think in full-scale system, if you use the DO control, the issue would be resolved easily. I think that's all my presentation. Thank you.
Hi, my name is Hannah Long. I'm here from Los Angeles County Sanitation Districts. Also on the call is Mike Liu from LACSD as well. He was here during the SideStream ANITA Mox pilot project conducted in 2014, so he'll be able to help with questions during Q&A. So this map shows Los Angeles County with the service area of the sanitation districts shaded in the darker gray color. No, that's not smog or smoke. I wish they'd use a different color there. But the shaded area is serves about 5.5 million people. We operate 10 water reclamation plants, shown with the blue triangles. And the yellow triangle at the bottom is the Joint Water Pollution Control Plant. It's our largest facility. It's where the pilot was conducted, and it's where I'm reporting to you from today. So the joint plant treats about 240 to 300 million gallons per day. It serves as the regional solids processing plant for 6 of the upstream reclamation plants. The effluent from the plant is discharged to the ocean. And the joint plant is a good candidate for SideStream anammox treatment because it's a large facility with regional solids handling, and there's a centrate stream from dewatered sludge from anaerobic digestion that's recycled to the head of the plant. On the left is an overview of the joint plant treatment process with the liquid stream across the top and primary and waste activated sludge feeding to the solids handling portion of the diagram at the bottom. Currently, there are no effluent nitrogen limits at the plant, but at the time we did the SideStream pilot, we knew that nitrogen removal could become necessary. At the joint plant, the centrate is recycled to the head of the plant and contributes about 15 to 20% of the influent nitrogen load. So targeting centrate for nitrogen removal makes a lot of sense to reduce the cost and size of any future addition of mainstream nitrogen removal capability to meet any potential future effluent nitrogen requirements. Our objectives for the ANITA Mox pilot were to determine whether the anammox process could work for joint plant centrate. Typically, centrate has high ammonia content, about 600 to 1500 milligrams nitrogen per liter, but our centrate is on the low end of that range, 600 to 900. So we wanted to test the efficiency of the process with relatively weaker centrate. And we also monitored a few additional metrics, removal rates normalized by the volume of the reactor, or VRR, and surface area of the media, or SARR. We also wanted to know the ease of operation and robustness of the process to common disruptions seen in the plant environment. The pilot included both MBBR and IFAS technologies. Larry went over some of this earlier, but I'll reiterate some of the points that were important to our operations. So on the left, the moving bed biofilm reactor, MBBR, develops 2 layers of fixed film on the media, anammox on the inner anoxic layer and AOB on the outer edge of the fixed film at the liquid interface. And this is important to deammonification because the production of nitrite by AOB is often the limiting substrate for anammox. And in integrated fixed film activated sludge, or IFAS, the fixed film consists of anammox and the AOB exists as flocks in the bulk liquid. So the conversion of nitrite to of ammonia to nitrite by AOB now happens in the bulk liquid. And this is an advantage because the oxygen and ammonia are now more accessible to the AOB. And this means the DO in the bulk liquid can be lower, which translates to lower aeration costs. So this favorable mass diffusion rate is the main factor influencing the potential cost advantage of IFAS. And the IFAS system does have an added clarifier to retain activated sludge, but because it can process a higher load than MBBR, IFAS could translate to much lower reactor size, and that would also mean lower costs. Pictured here on the left is the MBBR reactor, which was 950 gallons working volume and had a 47% media fill by volume. The media for both systems is pictured here. It was seeded anox caldnase K5 media. Like Larry said, it's about the size of a quarter or milk cap or POG, depending which generation you're from. The specific surface area is 800 square meters per cubic meter. On the right, the IFAS reactor is in the background. That had a working volume of about 800 gallons with a 37% media fill. And even though the IFAS reactor was smaller than the MBBR reactor, with its theoretical mass diffusion advantages, the IFAS was expected to perform as well as MBBR and potentially take higher loading, meaning have higher SARR due to its lower media fill. So here's a diagram of the pilot process with feed coming in at the left into a shared feed tank, and then that was pumped to the MBBR reactor and the IFAS reactor. There were only a few operating parameters, and that made it relatively easy to manage the pilot. MBBR operations were controlled with 3 parameters, the feed rate, the pH, and the dissolved oxygen. And IFAS had an additional parameter, the concentration of mixed liquor suspended solids retained with the clarifier. The sampling points to monitor performance were taken from the shared feed tank and the MBBR reactor effluent and IFAS effluent after clarification. Coming back to the solids handling portion of the joint plant process, the primary and waste activated sludge are sent to anaerobic digesters, and the digested sludge is dewatered in centrifuges. And the centrate, which remember is the feed to the pilot units, is sent to a dissolved air flotation process, or DAF, before it's sent back to the plant headworks. Today, the district operates high-speed centrifuges, which translates to lower solids in the centrate. And anticipating that, at the time of the pilot, the districts were considering eliminating the use of the DAF. And it was decided that the pilot would be tested on both pre-DAF and post-DAF centrate feeds. IFAS was only tested with the pre-DAF centrate feed, and that was due to the system having been started later than MBBR, and that was after it had already been shown with MBBR, spoiler alert, that the pre-DAF performed better than the post-DAF feed. So this shows the characteristics of the pre-DAF and post-DAF feeds. And as you can see, the post-DAF centrate was weaker in all these parameters, and that's because it's the underflow or liquid stream of the DAF after solids removal. and also partially due to the fact that the dilution from polymer processed water lowers the strength as well. And another parameter not shown here, it wasn't able to be monitored, is the polymer concentration, which was much higher in the post-staff feed. This table summarizes our performance metrics across the columns, removal efficiency and removal rate by volume and surface area. Along the left-hand side, going down, we have first the Denver pilot for MBBR, which was operated with our same MBBR reactor before our pilot started, and then each of our feed phases for the MBBR system, and last, our IFAS system. Focusing on total inorganic nitrogen, removal efficiency, which we were trying to hold constant across the feed phases, was pretty consistent across the board at 70%. And as you'd expect, the MBBR had similar removal efficiency, but a lower surface area removal rate with the weaker post-DAF centrate compared to the pre-DAF centrate. And the performance improvement here could have to do with the strength of the centrate, but it may also have to do with the high polymer in the post-DAF feed. As the pre-DAF MBBR operations were being optimized for deammonification, surface area removal rate increased to be comparable to the Denver MBBR system, although we weren't able to get those removal rates with as high a removal efficiency. But we're not salty about that. MBBR and IFAS had fairly similar removal efficiencies, although surface area removal rate was much higher for IFAS due to the two systems' different fill ratios. And this allowed much higher loading for IFAS and about 3 times the surface area removal rate. This plot shows on the y-axis the ratio of nitrate production to ammonia removal during each phase of the MBBR. The horizontal red line shows the stoichiometric ratio corresponding to anammox activity, with about 10% of nitrate produced per ammonia nitrogen removed. And ratios above this line suggest NOB activity as the nitrate produced increases, which we were trying to suppress because it competes with the anammox for nitrite, and that diverts resources from the more efficient deammonification pathway. Ratios at and below this line suggest anammox and possible denitrifier activity as the nitrate produced decreases relative to the ammonia removed. And you can see NOB activity seems higher until the pre-DAF optimized phase. And this could have had to do with us learning more how to operate the system, or the feed characteristics changing between the post-DAF and the pre-DAF phases. The final ratio for the pre-DAF optimized feed phase suggests NOB activity was under control and anammox activity was occurring. With the IFAS system, the nitrate produced to ammonia removed ratio shows minimal NOB activity over the 9 months of operation. And the ratio for IFAS was consistently close to the stoichiometric ratio for anammox, starting as early as 1 to 2 months into operation. In the IFAS system, the recycle stream retains the AOB flux. And this is essentially an extra operational parameter that adds flexibility because the capacity of the same size system can be essentially varied by how much mixed liquor suspended solids is retained. And the trend shows that up until about 3,500 milligrams per liter MLSS, each additional 1,000 milligrams per liter translates to an increase in about 2 grams more ammonia oxidized by surface area. System robustness was also important to us to show whether the process could be maintained under common plant disturbances, essentially with no operator interventions to speed up recovery. So a series of perturbances were imposed on the MBBR system: power outage, which cut off feed rate and aeration, and then variance in feed rate and aeration rate. And each perturbation lasted 24 hours. And the plot at the right shows the robustness metrics, which were the drop in performance and the time of recovery, both of which would be minimized in a more robust system. The performance metric on the y-axis was surface area removal rate for ammonia and total inorganic nitrogen. And the recovery threshold for calculating the time of recovery is shown with this dotted red line, and that was 95% of baseline performance. So to summarize the outcome, the system quickly recovered from a 24-hour power outage, and test 2, which was the lack of feed, which was meant to simulate a feed pump outage, also showed minimal effect in performance. Overfeeding by a factor of 2 was meant to simulate a flow meter issue, and that caused a 40% reduction in performance and took 40 hours to recover. Feeding excess polymer was meant to simulate an increased dose or a polymer metering issue, and that showed little effect for a slight increase, but for the longer and larger perturbance with the polymer concentration, it did cause a 39% decrease in performance and took 32 hours to recover. Lack of aeration meant to simulate a blower outage caused the most significant drop in performance, nearly ceasing ammonia removal, but it took 40 hours only to recover. And finally, simulating a DO probe issue over aeration by about 20% didn't cause an apparent change in performance. So to summarize the findings from the pilot, we found that relatively low strength centrate is treatable by ANITA Mox. The NBBR performed better on pre-DAF than post-DAF feed, but this could be because of nutrient load or the presence of polymer in the feed. IFAS had higher removal rates than NBBR, and that was consistent with the theoretical mass transfer advantage of IFAS. Both technologies seem to achieve anammox activity after getting NOB activity under control, and IFAS had a short acclimation period for this. The ANITA Mox process was also relatively robust under short-term perturbances. Even in the worst case, which was no aeration, the system fully recovered within 2 days. So with that, I think we can take questions.
All right, Anna, this was great. And actually, very nicely, Larry has been able to respond to, I believe, almost every question that is in the chat at this time. So thank you so much, Larry, for the sake of time. That was very, very helpful. There is one question that was sent to you and Michael. It looks like Michael is kind of answering it. You may want to chat in about it as well. But the question is, do you have any papers or articles on your robustness testing? So if you want to chime in with Michael, I'm not sure. We've got a couple more that's coming in as well.
Hi, Regina. On that question, we do have more details on that part of our work in our 2014 WEF-Tech paper. So I can send it to you for distribution for those interested.
Okay, perfect. We'll add it to the landing page with the recording. Great. And then I see one more, and that'll bring us right to the end of our presentation from Earl. Which parameters are considered in the recovery status of the system, BOD, TSS, etc.?
I guess that's referring to maybe our robustness testing. I mean, we looked at the ammonia and TIN removal rates, and essentially, since the system is aimed to remove ammonia and TIN, we thought that's the most direct metric.
All right. Well, I am looking through the chat, and it looks like we have covered everything. Well, I say we, but I'm going to give all acknowledgement to Larry, who was feverishly answering those questions in the chat to all of our attendees. So that's going to bring us to the end of today's presentation. I want to take this time to thank all of our presenters, Larry, Yang, Anna, and Michael, for a great presentation, and thank you to Viola for sponsoring today's event. This actually concludes today's eShowcase. Thank you all for attending. The recording will be available at webbuyersguide.web.org. We will send all registrants an email tomorrow with this link, and please visit our event calendar to sign up for a future webcast.
Thank you, everybody. Thank you. Bye.
Thank you.